Our topic in this lecture is the measurements. We have been mentioning measurements in some or the other context in several lectures earlier, but this will be one full formal discussion about measurements. So here we will be, there are several kind of measurements. One which we are familiar with, which is in the fourth postulate of quantum mechanics, that's the projective measurements. They are also called von Neumann measurements. So these are the measurements we have been talking about, which gives you the Born rule, which gives you the projective projection, the state collapse postulate, and the state after the measurement, those kind of things. So this is the measurement which we are familiar with, which comes in the fourth axiom of the quantum mechanics. This talks about the Born probability rule of the measurement and the collapse of the wave function after the measurement. So all the other kind of measurements which we will be discussing will be related to the projective measurement in some other context, but they are more general, so they can be treated in a slightly more general way. So the second one is like generalized measurements. So in these generalized measurements, we will talk about many measurements like indirect measurement, where we will not perform the measurement directly on the quantum system, but we will make it interact with another quantum system and perform measurement on the other quantum system. So in that way, we are not directly measuring the quantum system under consideration, but we are measuring another quantum system which we have coupled with the desired quantum system. Then there are POVMs. They are called projective positive operator valued measurements, and they contains mathematical structure of all the possible measurements on a quantum system. Then we will have coarse-grained measurements, and then we will have weak measurements. We may not discuss all these kind of measurements, but they will be surely touched upon through in these lectures. So let us start with the von Neumann measurement. So we have an observable A, which is a Hermitian operator, and it has eigenvalues AI and eigenvector AI, such that AI equals AI. This is its eigenvalue equation. All the observable must be the Hermitian operators. The property about Hermitian operators is their eigenvalues are always real, and their eigenvectors form an orthonormal basis. So we are choosing the eigenvector to be normalized, although the eigenvalue equation does not care about the normalizations, but we choose them to have norm 1. Then if we have a quantum system in the state psi, then the probability of getting the ith outcome, AI, the probability of getting AI is given by the Born probability rule, which is psi AI mod square. This is the Born rule. Second, once we have AI outcome, then the state psi collapses to the eigenstate AI. This is the collapse postulate. So the projective measurement says that if we want to measure an observable A, where small ai's are the eigenvalues and vector ai's are the eigenvectors of the observable A, then the probability of the ith outcome is given by the Born rule, which is psi inner product AI mod square. And after the measurement, the state of the quantum system collapses to the outcome eigenstate AI. We can generalize this treatment in the following way. Let us define a projector. Pn. So a projector is an operator such that Pn square equals Pn. This is the only definition of a projector. So any operator P, if it satisfies P square equals P, then it must be a projector. So for example, we are defining Pn to be An out of product An. It means Pn square, which is An, 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 An. This is a scalar here, which is inner product of An with itself. And since An is normalized, this is 1. We get An out product An, and this is Pn. Therefore, Pn equals An out product An is a valid projector. Now we can reformulate the two statements about the projective measurement, that is Born rule, that P of An psi An mod square. This can be written now as psi Pn psi. That becomes the new Born rule. They both are the same statement. We can see that when we substitute Pn, we get An out of product An psi, which is same as psi An in a product mod square. So we can write the Born rule in terms of the projected Pn. And the state collapse psi going to the projected state becomes Pn acting on psi divided by P of An square root. So this becomes the collapse postulate. So in this way, by defining the projector Pn, we can write both the statements of the projective measurement. If we have not a pure state but a mixed state rho, which is given by sum over n lambda n phi n out of product phi n. If we have a density matrix rho, then the probability of getting mth outcome will be sum over n lambda n am phi n am sum over n lambda n, the Born rule for each of the phi n am mod square, and the mixture, the statistical average over the mixture. This is how the probability of mth outcome, which is we are just writing as short form as Pm, but it's P of Am, is given by this. Now in terms of the projectors, it becomes sum over n lambda n phi n Pm phi n. And if we remember the cyclic property of the trace, this whole thing can be written as trace of Pm rho. This also can be written as expectation value of Pm. Similarly, here also the probability, this can be written as the expectation value of Pm. Pm here. So the probability of the outcome is the expectation value of the projector Pm. And the state collapse rho going to rho tilde after measurement becomes Pm rho Pm divided by P of small p of Am. And that's nothing but Am. So in that way, by defining the projector, we can reformulate the projective measurements in a much simpler, much concise way. But our definition of projector was P square equals P. This is the definition of projector. Then if we take, let us say, A1 out of product A1 plus A2 out of product A2, and let us call it P, then P square, since A1 and A2 are orthogonal, will also be A1 out of product A1 plus A2 out of product A2. So this is also a valid projector. So it means we can have a measurement setup where we have state coming in rho and outputs are there. And there can be scenarios where we cannot distinguish between, let us say, A1 and A2. So both of those outcomes gives you the same, both of those cases will give you the same outcome. Similarly, you can have bunch of other measurement measurement which will give you one click. So it means you will have P1, which is a sum of many sum over N1, AN1, and then you have other projector P2, which is sum over N2, AN2, and so on. You can have a set of many PNs which are not rank 1 projectors but more than rank 1 projector. They can be rank 1 or more projectors. These kind of measurements are called coarse-grained measurements. In some scenarios where we cannot distinguish between many outcomes, then we see these kind of coarse-grained measurements. For example, when we have two photons coming in with different polarizations, when we merge them on a beam splitter, then the output can be either a symmetric state or an antisymmetric state of the two photons in the polarization basis. So they are called singlet and triplet. In a linear optical experiment, we cannot distinguish between the singlet and triplet generally, unless we put some extra effort. So in those cases, the singlet state, which is given by the horizontal vertical minus vertical horizontal, the two photons being in different polarization, divided by √2. This is the antisymmetric state in the sense if we interchange the two photons, we get the negative sign out. And then we have a triplet where we have both photon in H or both photon in B, or one in H, other in B, plus one in B, other in H. This is the symmetric combination of the different polarizations. So this is a singlet, and this is a triplet, and this is a singlet state. Singlet state is the antisymmetric state, and triplet state is the symmetric state. Since the phonons are bosonic in nature, so in a linear optical experiment, we cannot distinguish between these three states. So whenever we have any of these states, we get the same click out, and when we have this, we get another click. So in that way, we have one projector. Let's call these states as 0 and this as 1, 2, and 3 state. So we have one projector P0, which is 0 order product 0, and other projector P1, which will be 1 projector 1 plus 2 projector 2 plus 3 projector 3. So in that way, we have some physical examples of when more than one orthogonal state being a part of a projector. So in these cases, what happens to the bond probability? So the bond probability P of n is still given by the expectation value of the nth projector. We do not care whether this projector Pn is rank 1 projector or rank 2 projector or rank 3 projector. What we mean by the rank is the number of non-zero eigenvalues. So since Pn square is Pn, then the only eigenvalues it has are either 1 or 0, because the eigenvalue should satisfy the equation satisfied by the operator. So Pn square minus Pn equals 0. So only 0 and 1 can satisfy this equation. Now, how many ones we have and how many zeros we have will tell us what is the rank of the projector. So when we have P to be An outer product An, then it's rank 1. When we have more than this, then we have rank 2, 3, and 4, depending on how many non-zero ones we have. So while defining this bond rule, this general bond rule, we do not care what is the rank of the projector under consideration, but the probability is given by the expectation value of Pn. So if it is a pure state, it becomes psi, Pn, psi, and if it is a mixed state, then it becomes trace of rho, Pn. This is for pure states, and this is for mixed states. Now the collapse postulate can be written as psi collapses to Pn psi divided by root Pn. If it is a pure state, and if it is a mixed state, rho goes to Pn rho Pn over root or over Pn. Till now, in terms of the representation, in terms of the expressions for the bond rule and the collapse state, there is no difference between rank 1 projector and rank 2 projectors, but or higher rank projectors. But one thing we have to see carefully is when Pn is a rank 1 projector, then if Pn is a rank 1 projector, then rho collapses to Pn rho Pn over small pn, which will be An out of product An. It means it's a pure state. It means rank 1 projectors project any density matrix rho to a pure state. But if it is rank more than 1, let us say 2, then we can write Pn to be An1 plus An2 then rho collapses to Pn rho Pn over Pn, which is not a pure state. It is actually a mixed state generally. Of course, if there is no component of An2 or An1 in rho, then we can get pure states also or nothing also. So in that case, things will be different. But in general, for the projectors more than rank 1, the projected state will not be a pure state, it will be a mixed state. Let us consider a set of projectors Pi such that Pi Pj is Pi delta Ij. It means if I is not equal to j, then it's 0. The product is 0. If I is equal to j, then it's a projector. So it's Pi square is Pi. And if sum over I, Pi is identity. Just let me remind you that identity is also a projector. It's a projector because identity square is identity. So identity is also a projector. And if sum over I, Pi is identity, then it's called informationally complete set. Set of projectors. So this is a valid measurement basis. So if we want to perform a complete measurement on a quantum system, we need to find one such set. One trivial example of or one regular example of such set is the set of the projectors AI that will amount to the regular polynomial measurement. This is the regular projective measurement we have been talking about from the beginning of this course. Then other can be coarse-grained measurement where more than one projector combine, more than one rank one projectors combine to make rank more than one projectors, and then we get a coarse-grained measurement. So one very trivial example is a set of just one element, which is identity, which is also an operator which is also a projector which satisfies all the conditions given above. So this measurement will yield nothing. So you have a state going in the setup and the state comes out. The probability of that happening is 1, and no information is captured about the system in this way. But this is a mathematically valid measurement. Next is measurement on composite system. Let us consider a bipartite system, HA tensor HB. For the sake of ease, we assume both of them are the same dimensional system and same basis they have. So an arbitrary state psi AB can be written as sum over ij, alpha ij, I tensor j. An arbitrary state can be written in this form, where I and j are the computational basis. What's the computational basis? Now, it's a bipartite system, it's a composite system. So we can think of it like there are two quantum systems, A and B, and they are in some joint state. This is just artistic representation of two entangled or joint quantum system. But they can exist physically apart from each other. So this can be in one lab and this can be in another lab. So there is a possibility that we perform measurement on subsystem B but not on subsystem A. So how do we represent such scenarios where we have a composite system and we perform measurement only on a subsystem of it? So partial measurements, let us call it. So let us say the measurement basis we are choosing on subsystem B is phi j basis. It's the orthonormal basis. It's a rank 1 projector, so it will amount to rank 1 projectors. So when we perform measurement on subsystem B, so the projectors we can think of, we can say that there are pi projectors or pj projectors, which are given by phi j out of product phi j. So the joint measurement of A and B will be the measure. In general, the joint measurement of A and B will be the measurement on subsystem A and measurement on subsystem B. Since we are not doing anything on A, the projector on A can be thought of as just identity projector on A, and PJs on B. So this is the basis in which we will be performing measurements. The total basis will be identity tensor PJ. We can see that sum over J, identity tensor Pj, equals identity tensor sum over J Pj. This is equal to identity tensor identity. So this satisfies the criteria of the complete, informationally complete basis in terms of projectors. Next, we can see that identity tensor Pi times identity tensor Pj will be identity tensor Pi Pj, which is identity tensor phi I phi j, and these are orthonormal bases. So this is delta ij, it becomes identity tensor Pi delta ij. So it satisfies, these set of projectors satisfy all the conditions of an informationally complete basis. So this is a valid measurement basis to perform on the subsystem, on the composite system AB. So the measurement will yield psi AB going to, after a measurement, identity tensor Pn on psi divided by root Pn, where root Pn is the probability of the outcome that is given by psi identity tensor Pn. Now we can see that, let us call it psi tilde, which is the projected state, will be 1 over root Pn sum over ij alpha ij, and there is a, let me write, identity tensor Pn I tensor j. This will be 1 over root Pn sum over ij alpha ij I tensor Pn is phi n out of product phi n j. This can be simplified, root Pn sum over ij alpha ij, we have phi n j, and we can take this also, and it is I tensor phi n. Now if we look at it carefully, this can be written as chi n tensor phi n, where chi n is 1 over root Pn sum over ij alpha ij phi n j and I. This chi n is the state of the subsystem A. subsystem A, and phi n is the state of the subsystem B after the measurement. So from the subsystem B point of view, after the measurement, the state collapsed to the eigenstate of the outcome, phi, because phi n was the outcome we got. And in response, the state of the subsystem A also collapsed to some state, and that state is given by chi n, which depends on the outcome of the subsystem A or subsystem B, that is phi n, and the coefficient, joint coefficient of A and B. So measurement on B affects the outcome of A also. That is one thing, that the measurement on B affects the state of A, and this is what is used in many of the quantum computation and information protocols. The quantum teleportation is performed using this principle. Another interesting thing to notice here is, after we perform measurement on subsystem A, the state psi AB, which was the initial state, does not matter what was initially the state. The outcome after measurement is a product state. This is a product state. Or in other words, it's a separable state, non-entangled. So a measurement on subsystem A, a projective measurement, rank 1 projective measurement on subsystem A yields a separable state between A and B. It destroys all the entanglement if there was any. We can generalize these results to the mixed state also, but those are trivial exercises. I'll recommend everyone to try those things at home. What will happen if, what would have happened if our projector was a rank 2 projector? It means Pn, let us say, was phi n1 plus phi n2, phi n2. So we want to explore the case when Pn is a rank 2 projector instead of rank 1 projector. In that case, psi AB will go to psi tilde, which is again given by 1 over root Pn sum over ij alpha ij I tensor Pnj. Now Pnj is phi n1 j plus phi n2 j. Let us call it P n1j phi n1 plus P R, let us say, R n2j phi n2, and we can substitute it there. So our psi tilde will be 1 over root Pn sum over ij alpha ij I tensor R n1j phi n1 plus R n2j phi n2. Now, the issue here is this state depends on both n, which is n1 and n2, and j. We cannot separate this in terms of like in n and j index. We cannot write this state which is independent of j. So in that way, we cannot write the whole state here as some chi tensor some phi n. Hence, this is an entangled state. Unlike the rank 1 projector, where we got a separable state, if the measurement is done in a coarse-grained manner, then the resultant state need not be a separable state. In fact, in general, it will be an entangled state. So this is the crucial difference between the rank 1 and rank 2 projectors when they are applied on a subsystem. Next, we will be discussing the indirect measurement. An indirect measurement consists of a system on which we want to perform the measurement. Let us represent the system with S. It's a Hilbert space Hs, and the initial state is rho S. And we want to perform measurement on rho S. To assist in the indirect measurement, we need a probe. Often we call it ancilla A. The Hilbert space of the ancilla is HA, and the initial state is rho A. We will choose rho A according to our convenience so that we can make the measurements easily and in a more effective way. Next is the coupling or interaction between A and S. The interaction between any quantum system is given by a unitary transformation, let us say represented by U. It's a unitary acting on HA and HS together in a joint manner. So the total Hilbert space H is HA tensor HS. So the unitary U belongs to the set of operators acting on H. So initially our total state rho is rho A tensor rho S. After the interaction, rho tilde becomes U rho A tensor rho S U dagger. And after that, we perform measurement on the ancilla. So to perform measurement, let us say we perform projective measurements without complicating things. So we choose the basis of the measurement to be n basis. So this is the orthonormal basis in the Hilbert space of the ancilla. When in the case of nth outcome, we get the outcomes, the state of the system and ancilla collapses to the following state: Pn tensor identity, U rho A tensor rho B, U dagger, Pn tensor identity over the probability. We'll talk about the probability Pn in some time, but the projector Pn is nothing but the projector over the state n. Let's say rho A, the ancilla state, is a pure state given by psi. In that case, rho tilde n becomes Pn tensor identity U psi tensor rho S U dagger Pn tensor identity. If we replace Pn with n and then we defined Kn to be n tensor identity U n tensor identity, then this becomes the operator acting on the Hilbert space of the system. This is the Krauss operator. We have discussed this thing in the completely positive maps. Then rho and tilde can be written as n outer product n tensor Kn rho Kn dagger. There was a probability Pn down there, and there is a probability Pn. Then Pn becomes the trace of rho tilde n, which is same as trace of Kn rho Kn dagger. So this is the probability of the outcome, of the measurement outcome. And this is the state after collapse. What we have done is we have extended our system of interest, the Hilbert space of the system, HS, to HS tensor HA or HA tensor HS. So we have made a simple system into we have converted a simple system into a composite system. And after that, we have utilized unitary transformation U to create interaction between system and the ancilla. Following that, we have performed a von Neumann measurement on the ancilla, And the effect of that can be seen on the system S in the following form, that the state of the system rho S goes to Kn rho S Kn dagger over Pn upon measurement. And this is a normalized state. So this is the result of an indirect measurement on the quantum system, S. This outcome happens with the probability Pn. So the total average outcome state of the system can be written as sum over n Pn times Kn rho S Kn dagger over Pn will be n Kn rho S Kn dagger. This is the average outcome state after the complete measurement. Kns are called measurement operators. The trace of the outcome state should be always 1 because it's a valid state. This implies that, which remains the exercise which we have already done also, that sum over n Kn dagger Kn should be identity. This is an additional condition over the measurement operators. Now what we have done, what is the difference between the projective measurement and the indirect measurement? In the projective measurement, we had a set of projectors Pn such that sum over n Pn equals identity and Pi Pj equals Pi delta Ij. They are orthonormal in some sense. So this is the projective measurements. In the indirect measurement, we have set of Kn such that sum over n Kn dagger Kn equals identity, and that's all. In the projective measurements, the probabilities Pn was given by expectation value of Pn, and the state rho n was, after the measurement, was Pn rho Pn over Pn. In the indirect measurement, the probability Pn is given by Kn rho Kn dagger trace, which also can be written as trace of Kn dagger Kn rho, or expectation value of Kn dagger Kn. And the state after collapse is given by Kn rho Kn dagger over Pn. In that way, there are certain differences in projective measurement and indirect measurements, but mathematically they are very much alike in spirit, and we can see that the projective measurements is a subclass of the indirect measurements. We can choose Kns in such a way that they become projective measurements. Till now, we have seen that given a unitary, which is the interaction between the ancilla and the system, and the initial state of the ancilla, and the measurement basis will yield a set of cross operators Kn or measurement operators Kn, which will which will give us the indirect measurements on a system, or generalized measurement on a system. The question can be asked, for a given set of measurement operator Kn, can we find a unitary operator U, a state of the ancilla, initial state of the ancilla psi, and the measurement basis n corresponding to Kn? So to answer this thing, we see that Kn was defined as n tensor identity, U psi tensor identity. Let us say n is the computational basis. It means vector n is defined as a vector of zeros with only one 1 at nth location. And let us say psi is the zero state. And we know that any arbitrary u which is acting on a composite system can be written as ij, I outer product j, tensor uij, where uij are the operators acting on the system helper. Or in other way, we can write it as u00, u01, u02, u10, u11, u12. These are all operators. So we have written U, capital U, as the matrix of matrices. Then we can see that n tensor identity, U0 tensor identity is UN0, which is by definition Kn. So if we had a U, then the first column of vectors, first column of operators is equal to the Kns we have as the measurement operators. So for a given set of measurement operators, we can choose a U such that the first column is the column of the measurement operators K0, K1 up to Kn, and rest of the matrix can be chosen arbitrarily in such a way. Let us say the rest of the matrix is R. We can choose R in such a way that U is a unitary. So we say R, we choose in such a way U is unitary. And this can always be done. So there is a huge choice in terms of R for a given set of measurement operators Kns, that U is a unitary. And here what we have assumed is the initial state of the system is initialized is 0 and the measurement basis is the computational basis. Of course, if we change these things, then U will also change. But since our task is to find the simplest U possible, we will choose the simplest initial state and simplest basis. But if the given problem demands something else, then we can choose those also, and our unitary matrix will also change. So in that way, for a given set of measurement operators K0, K1 up to Kn, we can always construct a unitary U for the initial state 0 and the measurement basis n, such that it gives you the indirect measurement.